did a lab a couple times ago, took some data, talked about some stuff. Do you remember what the big idea was for the lab? Ratios are going to be the same. Is that what we found in the data though? Not really. Okay.
What
So-
page?
Like 73. Alright, so yeah, the ratio, we expect the ratio should be the same. Not the same. We don't know what the right answer is. We're trying to propose what the right answer might be. The other big idea, because we were looking at a mass ratio, right? Mass is how much. But when we look at the formula, it would be nice to know, I think we look at the formula of something like H2O, it would also be nice to know how many.
2, 3,
To what?
hydrogen,
And
1 oxygen.
1 oxygen. Okay, yeah, so how many? Is mass going to tell us that?
No.
No. Why?
Because they're already all combined, so you're just going to know the mass of everything in total.
Yeah, maybe. We did a little bit of reading. We started doing a little bit of reading on the structure of the atom and where the mass of the atom comes from. Could mass tell us how many?
This means no.
Okay. Why no?
You combine 100 cookies in a jar, and then you weigh the jar with the cookies, and you didn't weigh it beforehand. How are you going to know how much the jar and the cookies are?
Oh, okay. We'll go with that analogy. What would have to be true about every single cookie?
They're all the same.
They all weigh the same. Do atoms all weigh the same?
No.
No. So mass would not be able to tell us how many because atoms don't weigh the same. And if you're thinking about the structure, why don't they weigh the same? Different numbers of protons. Good. All right. So if we had some kind of a relationship between mass and how many, well then that would be great. Right? Then we could convert. So that's what we're going to be talking about today. Did we watch the video of the silicon sphere? Okay, good. Then we'll go on. All right. So I'm guessing we left off on.
We left off on 80.
We left off on E.
I think so.
I
We
think
were
so.
talking about relating mass to numbers of atoms.
Okay, that's right. Because we were talking about all these masses. There was I don't remember. Oh, there was mass number. What is the definition of mass number? Yeah, okay.
Protons plus neutrons.
Protons plus neutrons.
Mr. Newton was curious if you have more fog machine for it or not.
I do. Okay, mass number of protons and neutrons. The big idea here, do all atoms have the same numbers of neutrons?
No.
No. And would we call it if an atom has a different number? Isotope. Okay. So when we know all the isotopes, then we come up with something. We come up with average atomic mass, which is the weighted average of all the isotopes. That's why when you look at your periodic table, hydrogen is 1.00794 because it's an average of the isotopes. Okay. Then we came up with something relative mass. Relative mass is all of the masses relative to carbon-12, because we needed a reference point to start. So relative mass is related to carbon-12. And then, so we're going to read about a new one today, molar mass. So all these give us an idea of the mass of the atom. Technically, are you ever going to need to use or know the definition of these?
Depends on what job you have.
Depends on what job you have. But for class, the only thing you need to know is the mass off of your periodic table, and that is the relative atomic mass. Okay? So if you have your periodic table, you should take that out. And tell me what the mass of nitrogen is. What's the mass of nitrogen?
7.
7? Or is that the atomic number?
11.
It's 14.0067.
14.006. Okay. What's the mass of, what's next, oxygen?
Oxygen
What's the mass of
is 15.9994.
15.99. Hey, why is oxygen one more than nitrogen?
Because it has more protons.
Has one more proton. Actually, it's like 2 more, right? It's almost 2. Yeah, it has 1 more proton. And probably 1 more neutron, right? Okay. Good. Right, let's go back to the brick feather analogy, right? How many bricks does it come? How many bricks to make a ton?
Just go like 40.
Some. How many feathers to make a ton?
Bazillion.
More, right? That's the idea. Okay. How many versus how much? Okay. So how do we do that? So let's Abby, do you want to start us off on the bottom of page 80, relating mass to numbers of atoms?
The relative atomic mass scale makes it possible to know how many atoms of an element are present in a sample of the element with a measurable mass. 3 very important concepts, the mole, Avogadro's number, and molar mass, provide the basis of relating masses in grams to numbers of atoms.
Okay. Gabe, you want to do them all?
What page are we on?
81. Top of page 80.
The mole.
The mole.
The mole is the SI unit for amount of substance. A mole is the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. The mole is a counting unit just like a dozen is. We don't usually order 12 or 24 ears of corn, we order 1 or 2 dozen. Similarly, a chemist may want 1 mole of carbon, or 2 mole of iron, or 2.567 mole of calcium. In the sections that follow, you will see how the mole relates to masses of atoms and compounds.
Okay. So this is a new idea, right? So the mole is the amount of substance that contains as many particles. How many particles? All right, let's think about that. If the mole were 10 particles, right? We could say, well, let's just think about this. Okay, hydrogen is something really, really light. If you had 10 pieces of hydrogen, that might weigh something.
10.
Would 10 pieces of helium weigh more?
Yes.
Because
It's times 2.
because it's heavier, because it has more protons of neutrons. Okay, because there's more mass. All right. So it doesn't really matter what number that is, right? We get the idea that if we had the same numbers, if we had 10 pieces of everything, some things would be heavier and some things would be lighter. That's an important idea.
So.
Say that one more time.
If you have 1,500 grams,
Oh, see, that's a good question. So, if we had 15 hydrogen and 10 helium, they might be close. So yeah, how many of a
30
light thing would we need
Many what?
to be the same mass? We get that they're going to be different mass, but how many would we need to make the same mass?
You need 3.
Okay. So the mole, how many particles? Well, Alex, you want to read how many particles? This is Avogadro. No, not avocado. Avogadro.
I think it's just because of the avocado.
Okay, Alex, you want to read about Avogadro's number?
The number of particles in a mole is experimentally determined in a number of ways. The best value is 6.022, 1,367 times 10 to the 23rd power. Means that exactly 12 grams of carbon-12 contains 6.022, 1,367 times 10 to the power 23 carbon-12 atoms. The number of particles in a mole is known as Avogadro's number, named for the 19th century Italian scientist Amandio. Avogadro's, whose idea was crucial in explaining the relationship between mass and numbers of atoms. Avogadro's number 6.022, 1,367.
Do you think he got bullied for his name?
Times 10 for the 23rd power is the number of particles in exactly 1 mole of pure substance. For most purposes, Avogadro's number is rounded to 6.22 times 10 to the 23rd power.
That's a big
Okay.
number.
Yeah. So how many particles are in a mole? 6.022.
Times 10 to the 23rd power.
Why are there so many?
A lot of decimals, I guess.
Because atoms are really small. Yeah. So it's going to take a lot of them to create a mole. And I guess maybe then the other question would be why so many? And the answer is really a practical reason.
Because that's what the human made of.
Well, can we measure out, if we were going to make water, is it easy for us to measure out 2 particles of hydrogen and 1 particle of oxygen and react them together to make a water molecule?
No.
No, that's not very practical, because there's no way for us to do that.
You can't trap 2 airs to make water.
So when we did this lab, how did we measure out the material?
We, well, it was solid.
It was solid, so we scooped it
And then we weighed it.
and we weighed it by mass. So like,
1-1.
practically we measure stuff
That's
out
the right one.
in grams. But does that,
I don't think you can measure
Tell us
air
how
by
many?
grams very good.
no, so we came up with this idea, right? If we scoop a scoop of a gram of a material onto the balance, how many is that? Well, it's going to be some fraction of a mole, right? It's going to be some fraction of this number. We're going to have half this or twice this much or whatever. I didn't take attendance, so. Oh, lunch count got me all bogged down, so.
Loser.
Sherry, she just likes to be late. So she's still not here, so I'm marking her absent and done.
She shows up late, like halfway through, like every single chemistry class.
Alright,
Probably.
so that's where we're gonna get. So is our scoop gonna be a mole or less or more than a mole, which is gonna relate to how many?
I think it's a mole.
You think it's a mole?
Yeah.
Okay, Blake, molar mass.
An alternative definition for mole is an amount of a substance that contains Avogadro's number of particles. Can you figure out the approximate mass of 1 mole of helium atoms? You know that a mole of carbon-12 atoms has a mass of exactly 12 grams, and that the carbon-12 atom has an atomic mass of 12 AMU. The atomic mass of a helium atom is 4.0 AMU, which is 1/3 of the mass of carbon-12 atom. It follows that a mole of helium atoms will have about 1/3 of the mass of a mole of carbon-12 atoms. Thus, 1 mole of helium has a mass of about 4 grams, 4.0 grams. How many you guys?
Sage.
The mass of 1 mole of a pure substance is called the mole mass of a substance. Mole mass is usually written in units of G/mole. The mole mass is an element is numerically equal to the atomic mass of the element in atomic mass units, which can be found in the periodic table. For example, the mole mass of hydrogen and lead is 6.94 grams per mole, while the molar mass of mercury Hg is 200.59 grams per mole, rounding each value to 2 decimal places.
Okay, so molar mass is the mass of 1 mole of a substance. Easy. How many particles are in 1 mole?
6.022 times 10 to the 23rd power.
So the mass of this many pieces is the molar mass, given in G per mol. What's G?
Grams.
Grams and mol.
Mole.
So molar mass in grams per mole is the mass of this number of pieces. Okay, so let's just get back just quickly. So if I gave you 1 mole of hydrogen, how many pieces is that?
6.
That equation.
Okay, let's pick something heavy like iron. If I gave you 1 mole of iron, how many pieces is that? Still be the same. Same number of pieces. Okay, does everybody get that idea? But it doesn't mean they weigh the same.
No.
No, we've already talked about they don't weigh the same, right? Hydrogen is going to be heavier or lighter? Lighter because it has less,
Protons.
good, and iron's going to be
Heavier.
because,
Mole.
okay. So we know that it's the same number of pieces, but they're not gonna weigh the same. Good, okay? And we know that hydrogen's going to be lighter, iron is going to be heavier, okay? Here's the nice thing about the way things work. Because the relative mass was related to carbon-12, and because the mole was also initially related to carbon-12, should the molar masses be related to each other? Yes, they should. Okay. And so, what do you think the mass of 1 mole of hydrogen would be in grams?
Big. Like long, but
No,
not like.
that's how many.
Oh.
But
Big.
what will its mass be? If you put that many pieces on the scale, what's the scale gonna read?
0.0.
1.01.
Close.
1.00.
1.00. 7, 9, 4.
Oh,
Granted,
it's still the weight of the
we're right.
element itself.
On our balances, is it gonna be 1.007?
No, it's gonna be like 0.
Oh, why, where'd you get that number from?
It's a
The atomic mass on the periodic table.
So if I gave you this many pieces of iron and I put it on the balance, what is its weight gonna be in grams?
it'll be
55.
0.845.
55,845 grams. Oh. So this confirms what we already knew. Hydrogen was gonna be lighter, iron was gonna be heavier because we know. Okay. Lead. 1 mole of lead. What's that gonna be in grams?
207.2.
207.2 grams. Yeah, okay. So the average mass and the relative mass, okay, and the molar mass, what number am I gonna look at on the periodic table? Okay. And so that's gonna be a very important number. So your periodic table is very important. Please do not lose it.
I don't even know what
Do you need another one?
I think it might be lost in here somewhere.
Did yours have yellow highlighter on it?
Yeah, probably.
Yeah, probably, or yeah.
I think I was
wasn't
writing
really
in
putting
highlighter on it.
highlighter on it. There's one in the book I was using yesterday. There was
Oh, this one?
Oh yeah, that's mine.
okay. So our understanding of mass and how many pieces very important. And so like this relationship is critical, and the more accurate we know this number, the more accurate any of our calculations are going to be. Okay? Because in our lab, we were looking at a mass ratio, which tells us some stuff, but does it give us the whole picture?
No.
No, right? If
Whole
we could
picture's
know,
huge.
if we could know how many, that would help us. Okay, and so this number is going to help us to understand how many. So we're going to watch a short video that kind of goes through mass, where mass came from, how we understand mass, and how we're trying to come up with a super accurate number here for the number of particles in 1 mole.